Section 3.1, Predicates and Quantified Statements. So a predicate is a sentence that contains a finite number of variables, and we are also then going to talk about the domain, which is the set of values that you can put into it. Pretty much everything we've seen mathematically is a predicate. So let's start with finding values that make it true. So here's my statement, x squared is greater than x. We are going to specify that our domain is the set of real numbers. And let's start by finding 2, 1/2, and negative 1/2. So if we plug in 2, I get a true statement. If I plug in 1/2, I get a true statement. However, if I plug in positive 1/2, I get a false statement. And negative 1/2, I do get a true statement. So as we can see here, sometimes it was true and sometimes it was false. Alright, so the true set, that is basically all of the values that work. So we have x is in that domain D, such that p of x, those are all of the values that make it true. So let's see what that looks like. And let's start with the domain of n is z positive, and we would like the set of all positive numbers, where I also have the predicate n is a factor of 8. So factors of 8, 1, 2, 4, and 8, and those are all positive integers, so those are my answers, and I've got them here in squiggly brackets. What if I've got the set of all just integers? Well, negatives will work as well in this case, so we still have the 1, 2, 4, and 8, but I do also now have negative 1, negative 2, negative 4, and negative 8. Alright, we've talked a little bit about universal quantifiers. Let's do a little more talk. Our symbol is a capital A that's been turned upside down, so I will read that as for all or for every. So if we have this little statement, we would read that as for all human beings, or for every human beings, for all human beings. X is mortal. Again, there's a couple ways we can phrase that. They all mean the same thing. We will also see this little symbol again. So remember that the symbol meant is contained in. So I would read that for all x contained in h, or just in h, as a shorthand there. And since most of the time we will be dealing with sets of numbers, it's going to make a little bit more sense than if we're talking about h being human beings. Alright, so let's take some statements here and figure out if they are true or false. So D is 1, 2, 3, 4, 5. So my statement for all x in D, x squared is greater than or equal to x. And I always recommend practice reading those aloud so that we get used to that notation. So here I'm just going to run through all of those values, and yes, they are all true. So I would say that one's true. Alright, my second statement, again, let's read that. For all x in the real numbers, or you could just say for all real x's, x squared is greater than or equal to x. And for counterexamples, we really only need one to show that it's not going to be true for all of them. There's obviously a couple things we could pick. Here I'm going to pick a half, and as we can see, 1/4 is definitely not bigger than a half. So that would be a false statement. Alright, let's look at the existential quantifier. This is a capital E that's been turned backwards, and we would read that as there is or there exists. So there is a person P, such that P is a student in Math 140. And again, we could also say there is a P in P, such that P is a student in math. Alright, now again, as a reminder, the universal for all means it has to work for every, but again, the existential means I only need one, and we're often going to see that term such that, because that tells us what property we are then going to see. Alright, let's determine if we've got some true statements. Again, let's read this aloud. So for all m in the positive integers, or rather, I'm sorry, there exists a positive integer such that m squared equals n. So it doesn't have to work for all of them. I just need one. And if I very deliberately pick one does work. For part B, E is 5, 6, 7, and 8. So there is an m in E such that m squared equals m. And here I've only got 4 of them, so I can run them out real quick. But none of them work. So even though it is a existential statement where I only need one, I was not able to find one that works. So that is a false statement. All right, let's talk about formal versus informal language. Now, when we talk, we usually talk pretty informally. For mathematics, though, we do try to be very formal because, again, we want to be clear so that everybody is talking about the same thing. So here, we want to rewrite so that that quantifier trails the rest of the sentence. So for any integer n squared is even. We could say 2n is even for any integer n. And similarly, there exists at least one real number x such that x squared is less than or equal to 0. I could write x squared is less than or equal to x for some real number x. We could also say for at least one real number x. Again, there's often more than one way to phrase that. All right, so here are some informal statements. Let's try to write them formally. All triangles have 3 sides. I'm going to write that as for all triangles T. T has 3 sides. And again, you can see a couple other ways I could write that as well. No dogs have wings. I would say for all dog D. D does not have wings. And again, you can see another way to write that as well. Some programs are structured. I'm going to write that there exists a program P such that P is structured, because that tells me I've got at least one of them, which is more or less equivalent to the word some. All right, let's get some universal conditional. A universal conditional, we've got the if-then, but you'll notice in front of it, I've got that for all x. So here is my very formal way of writing this. I have for all x in the real numbers. If x is greater than 2, then x squared is greater than 4. And so again, there's just the straight out how I would read that. And here's a couple ways I could try to phrase it. If a real number is greater than 2, then its square is greater than 4. And you can see a couple other ways to phrase that. They would all be acceptable. Generally speaking, though, we're going to want to be more formal rather than less formal. So that's not a type of problem we're generally going to see in this class. So let's try taking a less formal statement and writing it more formally, where we've got the for all and then if then. So if a real number is an integer, then it is a rational number. Again, there's a couple ways I could say it. Using my very formal notation, I've got for all x in the real numbers. If x is in the integers, then x is in the rational numbers. So these two statements are actually the same. It's just what type of notation I'm using. And you can see similar examples there for B and C. All right, can we ever get some equivalent forms here? Yes, we certainly can. So again, you'll notice for some of these we don't necessarily have that if there. We might kind of shorthand that a little bit and just have the for all x in D and then put the conclusion in there. And similarly, if we've got for all x in D, comma Q, again, you could also then write for all x, if x is in D, then Q of x. So we would say these two are equivalent. This one is just the slightly shorter version. So let's write this more than one way. All squares are rectangles. We could write for all x. If x is a square, then x is a rectangle. We could say for all square x, x is a rectangle. All right, let's look at rewriting existential statements. And quick little definition here, a prime number is an integer greater than 1 whose only positive integer factors are itself and 1. Do note that 1 is not a prime number. So here's my statement. There is an integer that is both prime and even. And we can write there is an n such that prime n and even n, remember that is my and. I could also write there is a prime number such that even n, or there is an even number n such that prime n. So again, there's a couple ways I could rewrite that. Finally, implicit quantification. You'll notice we do not have any of the words all, every, any, each. Those are things we like to say so that we can be, again, as clear as we possibly can. And that's why we do often do the rewrite. Again, the existential, we don't always, strictly speaking, write it out. We'll just say the number can be. So again, we would often rephrase that as there is a number, and then go from there. Now, most of our questions, we will see that formal language to begin with, but we do want to be aware that these exist. So I've got three statements: Q of n is a factor of 8, R of n is a factor of 4, S of n is less than 5, and n is not 3, and our domain is the positive integers. So let's use these symbols to indicate true relationships. So let's first set out what is R of n. That is going to be 1, 2, and 4, since we're only in the positive integers. So we would say that n is a factor of r implies n is a factor of 8. So R of n implies Q of n. And similarly, the true set of S of n is 1, 2, and 4. That is exactly equal to R of n. So you'll notice I've got an arrow pointing both directions. And similarly, I can write S of n and then my arrow pointing to Q of n. And that is everything in section 3.1.